Greetings, dear viewers. It's no news to any of us that humanity has been confidently and successfully polluting the environment for a couple of centuries now. One of the contributors to pollution is vehicles. They emit exhaust, wear down their tires on the road, produce dust from brake pads, and so on. And during their production, a certain amount of carbon monoxide, too, hated by environmentalists, is also released into the atmosphere. In the modern world, an environmental agenda has emerged for some time now, and many are trying to find a solution to the problem of excessive pollution of nature. Some are passionate about electric trains, others build gas generator units, and others convert cars to run on alcohol fuel. Some put their hopes in nuclear fusion, while others see hydrogen as the fuel of the future. And that's what we're going to talk about today. We'll dig into history, find out when humans first obtained this chemical element in its pure form, who invented the first hydrogen engine, and so on. We'll look at the advantages and disadvantages of this type of fuel, both from the production side and from the application side. And together, we'll try to clarify whether hydrogen is really the bright future that you are painting for us. You're on the Cross Moda channel. Enjoy watching.
By 2050, only electric and hydrogen cars will remain in South Korea.
Right now, we're making hydrogen engines even more eco-friendly. However, the country lacks enough hydrogen fueling stations.
Is this the future? Because it's the world's first mass-produced hydrogen fuel cell car?
Hydrogen, chemical symbol H from the Latin hydrogenium, is a chemical element in the first period of Mendeleev's periodic table of chemical elements, with atomic number 1. Hydrogen is the most common chemical substance in the universe. It makes up 75% of the mass of all baryonic matter. Stars, except for compact ones, are mainly composed of hydrogen plasma. Hydrogen is the lightest element in the periodic table. However, despite being so common in the universe, it is difficult to find pure hydrogen on Earth. This element readily forms covalent bonds with most nonmetals. Therefore, in our reality, it exists in the form of organic and inorganic compounds. Water is the most vivid example among inorganic compounds. Since gaseous hydrogen is extremely light, it gradually escapes from the Earth's atmosphere. Every second, under the influence of the solar wind, the Earth loses 3 kilograms of hydrogen, which in the distant future will lead to the drying out of the planet.
Hydrogen, oxygen.
Since most of the hydrogen on Earth is found in molecular compounds, it was discovered relatively late. The release of a flammable gas during the reaction between metals and acids was observed as early as the 16th century, that is, during the formation of chemistry as a science. In 1766, the famous English scientist Henry Cavendish conducted a reaction between zinc and hydrochloric acid and studied the flammable gas produced as a result of the reaction. Cavendish called it inflammable air. When burned, this gas produced water, but Henry did not draw the correct conclusions from his research and did not realize that he had discovered a new substance. The French chemist and naturalist Antoine Lavoisier, together with the engineer Jean Meunier, used special gasometers to synthesize water in 1783, and later analyzed it by decomposing water vapor with heated iron. Thus, the scientists were able to reach the correct conclusions. They established that flammable air is not only a component of water, but can also be obtained from it. In 1787, Lavoisier suggested that the gas understudy was a simple substance, and accordingly belonged to the group of primary chemical elements. He called it hydrogen, which literally means water former. And the combustible properties of this light gas could not go unnoticed by scientists and engineers. Moreover, with the development of applied sciences, the first prototypes of internal combustion engines began to appear, and at first, all sorts of things were used as fuel for them. Hydrogen has long been considered one of the most promising types of fuel. Its combustion is extremely efficient, and the result is water vapor. And that's great news for environmentalists. The specific heat of combustion of hydrogen is about 120 to 130 megajoules per kilogram, which is several times higher than that of hydrocarbon fuels. Here's a quick table I put together that shows the most common types of fuel, along with their density and specific heat of combustion. Pay attention to the density. For example, methane is 7.5 times denser than hydrogen. So what conclusion can we draw from this? It's quite simple. Using higher hydrocarbons makes the storage tank more compact, which is an important detail for vehicles. Let's delve a little into history. The first engine running on hydrogen was invented in 1806 by the French inventor François Isaac Derivas. He produced hydrogen using water electrolysis. His engine was the first to use solutions that are still used in modern internal combustion engines, such as the piston group and spark ignition. However, the crank mechanism was not yet included in the design. In 1807, Derivas equipped an experimental vehicle with such an engine, and in the same year, he applied for a patent called the use of the explosion of lighting gas or other explosive materials as a source of energy in an engine. I want to emphasize that the first internal combustion engines were quite primitive and unreliable, and it was considered a success if it could run on its own for at least 20 or 30 seconds. And only thanks to numerous attempts, improvements, and the work of hundreds and thousands of engineers did humanity eventually arrive at engines that could last for 1,000,000 kilometers. The first patent for a hydrogen engine was issued in the United Kingdom in 1841. In 1852 in Germany, they built an internal combustion engine that ran on an air-hydrogen mixture. 8 years later, in 1860, the French inventor Étienne Lenoir designed the Hippomobile, the first versions of which ran on hydrogen. The fuel gas was produced by electrolysis, which is where the name Hippomobile comes from the ancient Greek hippos, meaning horse, because the vehicle constantly needed to drink. Later, Lenoir's car was adapted to run on illuminating and coal gas, and these models gained some recognition among buyers. For example, one of Lenoir's cars was made for the court of the Russian Emperor Alexander II. In 1862, Lenoir tested the Hippomobile, driving it for 18 kilometers near Paris. Taking into account the stops along the way, the trip took 3 hours and required a huge amount of fuel. In 1933, the Norwegian oil, gas, and metallurgical company Norsk Hydropower converted one of its small trucks to run on hydrogen. The chemical element was produced by reforming ammonia and supplied to the engine. In Leningrad, during the blockade, about 600 balloons operated on an air-hydrogen mixture. This solution was proposed by military engineer Boris Shkelish to solve the problem of gasoline shortage, which had already become scarce by the autumn of 1941. He also converted about 200 GAZAA trucks to run on hydrogen, as well as all the winches in the city. In 1942, Shkelish was sent to Moscow to implement his technology in the Moscow air defense units. In the winter of 1941, junior military technician was awarded the Order of the Red Star for his submitted R&D proposal. However, everything we've discussed so far was based on the combustion of hydrogen in the cylinders of an internal combustion engine. But there is another way to generate energy: hydrogen fuel cells. They directly convert the chemical energy of the hydrogen oxidation reaction into electric current without the combustion process. By the way, water will also be produced at the output of such a device, and you'll be surprised at how long ago such a fuel cell was invented. As far back as the year 1839. That's when the Welsh inventor Sir William Robert Grove developed the Grove cell. William experimented with different types of electric batteries and discovered a potential difference on platinum plates immersed in a mixture of hydrogen and oxygen. It was only in the 1920s that research into fuel cells led to the development of solid oxide fuel, increased efficiency, and output levels that could be considered suitable for practical use. In its quest to generate electricity through chemical reactions, the American company Allis-Chalmers, which produced machinery for various industries such as construction, agriculture, resource extraction and processing, as well as power generation and transmission. In 1951, it began research on hydrogen fuel cells. On October 15, 1959, engineers from the Alice Chalmers Research Division presented a hydrogen fuel cell tractor. This fuel cell tractor plowed a field of alfalfa with a two-bottom plow. It was an amazing sight. Everything happened without the roar of engines, without a cloud of exhaust. The tractor housed 1,008 fuel cells combined into 112 blocks, each with 9 cells, arranged in 4 units, which generated power for a standard Alice Chalmers 20 horsepower direct current motor. For mass production, this tractor was extremely expensive, but it became a stepping stone that took the company to a new level. Alice Chalmers developed fuel cells for the space program, and the United States military also contracted for some experimental fuel cell equipment. Subsequently, in the 70s, the company shut down the division and sold it to Teledyne Corporation due to funding cuts. After conducting tests, Alice Chalmers transferred the fuel cell tractor to DAR at the Smithsonian Institution. The English engineer Francis Bacon, building on previous research, expanded the concept of the hydrogen fuel cell. His final design, the Bacon cell, was improved in 1959. Its fundamental principles were used in the development of fuel cells employed by National Aeronautics and Space Administration in their rockets. Hydrogen fuel cells for space had an interesting side effect. In addition to generating electricity, they produced water, which astronauts later drank. I wonder if there will be commenters under the video who believe that humans have never been to space. And it was National Aeronautics and Space Administration's involvement that made hydrogen fuel cells a viable commercial resource. In the 1960s, the agency funded more than 200 research contracts, which gradually led to the creation of more compact and efficient hydrogen fuel cells that could be installed in cars, airplanes, and other vehicles. The first hydrogen fuel cell car was the Electrovan by General Motors in 1966. The Electrovan was the brainchild of Dr. Craig Marks, who led most of General Motors' advanced engineering projects. Marks, together with 250 employees, developed the Electrovan for more than 2 years. The Electrovan used a fuel cell made by Union Carbide, which ran on supercooled liquid hydrogen and liquid oxygen. Today's fuel cells use less pure oxygen, which is found in the surrounding air. The Electrovan had one large tank for hydrogen and one for oxygen. There were about 168 meters of piping running through the vehicle, and in fact, the 6-seat van was so packed with equipment that it could barely fit 2 people. The van was capable of driving up to 193 kilometers on a single fill-up. It was built as a one-off technology demonstrator, and for safety reasons, was only driven within the factory grounds. General Motors had plans to equip and release a small batch called the Electrovan with a similar setup, but the system was enormous. There were also multiple instances of hydrogen and oxygen leaks on the Electrovan prototype, and once there was even an explosion of the hydrogen tank. Interest in hydrogen increased during the fuel crisis in the 70s.
When an organization of the petroleum exporting countries' oil embargo led to an international shortage and rocked the
In the 70s, work was also being done in the Soviet Union to create prototypes of equipment running on hydrogen. During this period, various organizations, scientific institutes, and automotive institutes created prototypes of cars running on hydrogen and gasoline-hydrogen mixtures. Among them were Zhiguli, the 412th Moskvich, the 24th Volga, Gorkovsky Avtomobilny Zavod, 69, the RAV, and Ulyanovsky Avtomobilny Zavod, minibuses, as well as the Zavod imeni Likachova, 130 truck. I'll say a little more about a couple of these prototypes. In 1976, specialists from the Institute of Mechanical Engineering Problems of the Academy of Sciences of the Ukrainian Soviet Socialist Republic in Kharkiv built an experimental Moskvich 412 car with a power unit running on hydrogen. In addition to the usual gas tank, a mini reactor containing catalytic elements was installed on the Soviet sedan. Water passing through this reactor was split into hydrogen and oxygen, which then burned in the cylinders of the internal combustion engine. It is noteworthy that the fuel system for supplying hydrogen was installed in parallel with the standard gasoline system. Starting from 1976, we worked on converting the RAF 2203 minibus to run on hydrogen fuel. Starting from 1979, it underwent laboratory and road tests as well as trial operation. Soviet scientists noted that the gasoline-hydrogen system showed low exhaust toxicity. Carbon monoxide was reduced by 23 times and nitric oxide by 5.3 times. Fuel efficiency was also noted. Several hydrogen minibuses served the Olympic Village in 1980. Work was also underway in the Union on a hydrogen system for aviation. It was tested on a prototype Tu-155.
A production car engine runs on hydrogen just like it does on gasoline.
In 1979, the first BMW car with a hydrogen engine appeared. This experimental prototype was created by engineers together with the German Aerospace Center based on the 520/4 model. On the outside, the car was hardly different from its gasoline counterparts, but its four-cylinder engine ran on hydrogen. However, after the fuel crisis ended, the idea of alternative engines was forgotten until the 2000 SE. The 21st century led to a significant boom in research and implementation of hydrogen fuel cells. In 2004, the German fleet tested a hydrogen-powered submarine, and China tested the world's first hydrogen train in 2015. In 2007, the same BMW released a limited series of Hydrogen 7 cars that could run on both gasoline and hydrogen. But the car was not cheap, and the 8-kilogram gas cylinder was only enough for 200 to 250 kilometers. The first mass-produced car model with a hydrogen engine was the Toyota Mirai, released in 2014. Today, hydrogen models exist in the lineups of major car manufacturers such as Honda, Hyundai, Audi, BMW, and Ford. Even a Russian premium car as a prototype was equipped with hydrogen fuel cells. And after 10 minutes of my story about various prototypes and the research of scientists in the field of hydrogen fuel, work on which has been going on for at least 100 years, a perfectly logical question arises. Why the heck is humanity still driving on gasoline and diesel? Well, lately a bit on electricity too. Why, despite many years of work and research, does sacred hydrogen still remain the fuel of the future and not of today? Let's figure out what's wrong with hydrogen. How does hydrogen fuel look to the average person who hasn't really delved into the topic and has only heard about it from television news, eco-propaganda, on the internet, reels, and shorts? Hydrogen is the fuel of the future. It's eco-friendly. It's an inexhaustible resource. Not a single polar bear, pink flamingo, or unicorn will die because of such a car. And if you're thirsty, you can just suck on the exhaust pipe of this vehicle, because pure water comes out of it. Here's the approximate context. Now let's go backstage and break it down step by step. The first obvious problem with hydrogen is that you can't just extract it from the earth, the ocean, or the atmosphere. It's not like natural gas or oil where you drill a well and pump the stuff through pipes. Hydrogen on Earth is bonded in molecules with other substances, and you need to apply a certain amount of energy to break those molecules apart and get pure H2. There are several methods for producing hydrogen: electrolysis, voltage is applied to electrodes, and water is split into hydrogen and oxygen. This method is also possible with aqueous solutions of salts. There are several chemical methods: methane conversion with steam at 1000 degrees Celsius, passing water vapor over hot coke at about the same temperature, catalytic oxidation of methane with oxygen, cracking and reforming of hydrocarbons during oil processing. Well, and in laboratories, hydrogen is produced in very small quantities as a result of the reaction of metals with acids and alkalis, with zinc and aluminum. As of 2019, 75 million tons of hydrogen were produced and accordingly consumed worldwide. Most of it is used in oil refining and in the production of ammonia, 3/4 of this amount is produced from natural gas, and almost all the rest is obtained from coal. And only about 4% is produced by electrolysis. And what is it? After all, there are so many videos from home do-it-yourself enthusiasts who use electrolysis to split water into hydrogen and oxygen. As an entertaining pastime and for producing small amounts of hydrogen, that'll do. But let's look at the energy aspect of the process. At the beginning of the video, you remember that burning 1 kilogram of hydrogen releases 120 to 130 megajoules of energy. Now let's calculate how much electricity we need to spin to produce 1 kilogram of hydrogen by water electrolysis. It comes out to about 50 to 55 kilowatt hours. If you convert that to megajoules, it turns out to be 180 to 198. So from an energy standpoint, this is an unprofitable process. By the way, do you know how much carbon monoxide, 2, is emitted when producing those 75 million tons of hydrogen used in global industry every year? 830 million tons. But how does that happen since hydrogen is so clean and innocent? Look, there are at least 4 types of hydrogen based on how it's produced and the associated carbon footprint: brown, blue, gray, and green. Brown, as you might guess, is the dirtiest. It's produced by gasifying lignite coal. As a result, synthesis gas is formed, a mixture of carbon monoxide, 2 carbon monoxide hydrogen, methane, and ethylene, as well as a small amount of other gases. Blue hydrogen is produced by steam reforming methane, but only if the carbon is captured and stored. This method is quite expensive. Gray hydrogen is produced by steam reforming methane, and more than 70% of our hydrogen is of this type. Natural gas is used as the raw material for this reaction. Green hydrogen is the cleanest and is produced by electrolysis, provided that the electricity comes from renewable energy sources such as wind, solar, and hydropower. And there are no carbon monoxide, 2 emissions, although for some reason they don't take into account the emissions produced during the creation and installation of these facilities. Different production methods lead to different costs of the final product. With the most common method, it's gray hydrogen. The cost of 1 kilogram of H2 ranges from $1.5 to $3 United States dollars. With more expensive methods, the price can reach $10 per kilogram. There is also the so-called white hydrogen. It is produced by natural geological processes. This type of hydrogen was first discovered in 1979 in the mines of Mali. At the moment, scientists and engineers are puzzling over the possibility of extracting such a resource. However, since this gas is extremely volatile, the task will not be easy. So, we've briefly figured out how to obtain it. Now it's time to talk about storage and transportation. You do remember that hydrogen is extremely light. So in its liquefied state at a temperature below minus 253 degrees Celsius, its density is 71 kilograms per cubic meter of volume. For comparison, the same volume of water weighs 1,000 kilograms. Storing liquid hydrogen involves inevitable and quite significant losses due to its evaporation, up to 0.5% per day from tanks with a volume of up to 50 cubic meters. Larger tanks tend to have lower losses of this substance. Also, storing liquid hydrogen requires strict temperature control of the tank and high energy costs. In real facilities for producing liquid hydrogen, the energy costs range from 30 to 50% of its calorific value. Therefore, this method is very expensive. In the case of storage in a gaseous state, hydrogen needs to be compressed to higher pressures than methane, for example. And again, because of the low density. After all, in a car, you can't really go wild with the size of the fuel tanks, but you still need to have a certain driving range on a single fill-up. That's why in modern hydrogen cars, the tanks are filled to a pressure of about 700 atmospheres. Under these conditions, you can store 39 kilograms per cubic meter of volume, but the strength requirements for the tanks are also very high. There is also a third option for storing hydrogen, metal hydrides. I'll explain quickly and simply how this works. The H2 molecule is about 1.2 times 10 to the minus 10th meters in size. The size of a hydrogen atom, that is, a single proton with one electron moving around somewhere, is 0.529 times 10 to the minus 10th meters. The proton itself is 2.5 times 10 to the minus 13th meters. So one proton, the nucleus of the atom, is 211 times smaller than the atom itself. Hydrogen has a very interesting property. When it comes into contact with certain metals and alloys, it loses its electrons, and what's left are pure protons, which then become embedded in the crystal lattice, and you can fit a lot of them in there. This reaction is reversible, which makes it possible to carry out loading and unloading cycles in metal hydride storage systems. With this method, the packing density can reach up to 150 kilograms per cubic meter. But the energy costs amount to 30 to 40% of the calorific value of hydrogen. There are also options with absorbents, organic carriers, and so on. It's worth remembering that any of these methods requires energy costs. Hydrogen needs to be liquefied, compressed to enormous pressure, injected into metal, and then extracted back, and so on. And at the moment, in the context of storing hydrogen on a vehicle, nothing more efficient has been invented than pumping 700 atmospheres into a cylinder. The losses are only about 10%, and there is no magical breakthrough expected in the industry. Transporting hydrogen is another challenging task, and the problem lies in the hydrogen itself. It's the simplest and smallest element. It can seep through places where methane or ammonia would never leak. This leads to a high fire hazard, and hydrogen flames are barely visible on a clear day. Because of these properties of the most common element in the universe, hydrogen pipelines and storage tanks have much stricter requirements for sealing and material quality. Therefore, in today's reality, most hydrogen is produced at the point of use, that is, near petrochemical plants and ammonia production facilities. The longest pipeline at the moment is located in Germany and Belgium and is only 400 kilometers long. Experimental studies on the possibility of transporting hydrogen using steel pipelines for natural gas have shown that hydrogen losses from the system are 3 to 3.5 times greater in volume than natural gas losses. Moreover, delivering hydrogen through a pipeline requires 3 times more energy than delivering natural gas for the same amount of transported energy. It's worth mentioning a bit about the infrastructure. There are currently few hydrogen fueling stations in the world. All the difficulties with storage, transportation, fire, and explosion hazards also apply to them and affect their cost. And building the infrastructure, which is very expensive and may not even pay off, is really not easy. In the context of the difficulties of transportation and storage, all dreams of a hydrogen economy assume small and distributed hydrogen production systems, which leaves us with only one realistic option: electrolysis. Such production should be handled by competent organizations with strict adherence to safety regulations, occupational health, and so on. You can't just hand over hydrogen production to the masses. Personally, I wouldn't want my neighbors producing H2 at 600 or 700 atmospheres of pressure using solar panels. To hell with neighbors like that. And finally, let's look at the efficiency of hydrogen-powered cars themselves. As you understood from the narration, there are 2 ways to extract energy from hydrogen and turn it into motion. In the first case, we have a classic car with an internal combustion engine, and the air-hydrogen mixture burns in the cylinders. But there are problems. If you don't change anything in the internal combustion engine, the power drops by 20 to 35%. If you make changes to the ignition system, you can even achieve 10 to 15% more power. However, in this case, the temperature in the combustion chamber increases, and so does the risk of burning out the valves. You remember that hydrogen is extremely fine. So, at the temperatures and pressures in the combustion chamber, it can penetrate the metals the engine is made of, which reduces their strength characteristics. In short, a hydrogen internal combustion engine wears out much faster, and engines that last 1,000,000 kilometers are out of the question. So internal combustion engines are poorly suited for running on hydrogen. And I wouldn't get too excited about Toyota's presentation of their new hydrogen engine. And finally, in today's reality, when 95% of all H2 comes from fossil hydrocarbons like gas, oil, and coal, it's more economical to just burn those hydrocarbons directly in the engine. Now it's time to talk about fuel cells. Basically, we have a hybrid car where hydrogen is converted into electricity, This means that for real-world use on the roads, in addition to the hydrogen system, you also need a battery, which will be required for the fuel cell's own needs and other car systems, as well as for smoothing out the production and consumption of electricity during driving and regeneration. Modern fuel cells have an efficiency of 50 to 55%, and that's not far from the theoretical limit of 83% for an ideal fuel cell, according to the Gibbs function. So let's take an efficiency of 50%. That's better than an internal combustion engine. But wait, after calculating all the losses in the chain, starting from solar panels and wind turbines, water electrolysis, transportation, hydrogen storage, electricity generation in the fuel cell, and losses in electric motors, in the end, we get an efficiency of about 22%. And this chain is calculated for green hydrogen. We don't want to kill the planet with emissions. And modern car internal combustion engines have an efficiency of 30 to 35%. It turns out to be the same efficiency as electric cars in the chain from burning fuel at a power plant to moving through space. Do you remember Asafiev's calculations in the episode about Tesla? And this efficiency was calculated under the conditions of storing hydrogen in a gaseous state in a cylinder. But if you calculate it for metal, hydrides, or liquefied hydrogen, the efficiency drops to 13 or 14%. The only advantage of a hydrogen car is a higher refueling speed compared to electric battery vehicles. But is it worth such low efficiency? And also, fuel cell cars cost as much as a wing for a Boeing, because the cells use platinum and palladium, which are not the cheapest metals on the market. It's also important to remember that fuel cells require very pure hydrogen. For example, carbon monoxide impurities, which are present in brown, gray, and blue hydrogen, significantly reduce the efficiency of the cells. Carbon monoxide acts as a so-called catalytic poison for them. There is a rather old video in which Elon Musk calls the concept of a hydrogen car with fuel cells foolish.
There is a debate about the efficiency of hydrogen fuel cells, as I believe that this concept is extremely foolish.
And yes, on the one hand, Musk is quite a talker. The value of several stocks can depend on just a few of his words, and he needs to promote his electric Teslas. But on the other hand, Elon is not a stupid guy. He knows how to calculate compound interest and understands that efficiency can't be greater than 1. After the numbers mentioned in the previous chapter, and after I figured them out a bit myself, it becomes clear that the guy who wants to fly to Mars isn't saying such nonsense after all. People who are enchanted by the idea of a bright hydrogen future are probably already spitting at their screens and writing angry comments. I love you too, guys. And of course, I got paid off by the oil guys. Yesterday, the Gazprom people brought me a suitcase. And the day before that, Shell dropped by for tea. Unfortunately, that's not how I wish it was.
You can claim as much as you want that now they'll put up a bunch of wind turbines and solar panels, and all the energy will be green and everything will be fine.
And then there will be plenty of green hydrogen. And it will become cheaper, and hydrogen cars will become more widespread and cheaper to produce, and the refueling infrastructure will follow. But all of this comes down to such crazy financial costs that even under ideal conditions, without crises, wars, or disasters, such a transition would take at least half a century. In theory, white hydrogen could help the hydrogen future a little. In Kansas, they seem to be planning to drill a test well in 2025. Whether it will be possible to establish commercially viable extraction, time will tell. I think it will be very difficult. As you can see, the devil is in the details, and he's not really hiding that much if you look even a little closer. In fact, we have a technology that has already hit physical and chemical limitations. A technology that politicians and populists mention to gain popularity ratings and points before elections. A technology that men in suits and ties use as a pretext to spend budgets. And ecology is just a beautiful cover, something like that. Maybe a bright energy future will come someday, but definitely not tomorrow and not in 10 years. Many people will probably argue that it's those damned oilmen who are preventing alternative technologies from developing. I have a counter-argument for you. The big shots in the energy business have every opportunity to take alternative developments, patents and scientists under their wing so they can later milk a different cow. That's all. If you can't prevent it, lead it. Who said that, Machiavelli or Suvorov? I can't remember. In this world, everything is subject to logic and economic feasibility. So I don't know about anyone else, but I'm going to roll out my Yamaha, fill up the tank with 95, and go enjoy myself. That brings my story to an end. You know yourself what to do during or after watching. There's the subscribe button a bit to the right. You can give a thumbs up or down, and you can write comments below. You can also share this video with someone you know for fun or for their information. This was Cresmota Channel with you. See you next time.